There is a rule on the Dalton Highway that most people have never heard of. It is not written in any safety manual. It is not posted on a sign. It is not part of any official regulation. But every experienced driver who has hauled freight through the Alaskan interior in the middle of winter knows it by instinct. The same way they know to keep moving through a whiteout and to never, under any circumstances, park too close to the edge of a ridge when the wind is building from the north. The rule is simple. If the temperature drops below a certain point, you do not turn off the engine. Not when you stop to rest. Not when you park for the night. Not when you are sitting in a gravel pullout watching the northern lights move across the sky in curtains of pale green and violet. Not even when you need to sleep. The engine stays running. Always. And if you have never driven a truck through temperatures that drop past minus 50 degrees Fahrenheit, that might seem like a strange choice. A waste of fuel. An unnecessary risk. Something a driver might do out of superstition, or habit, or simple stubbornness. But it is none of those things. It is survival, and the science behind it, the engineering, the decades of hard-won knowledge embedded in that one decision, tells one of the most remarkable stories hidden inside the working life of a professional driver in the American Arctic. This is that story. If you are watching on television and this is your first time finding this channel, consider sharing this with someone who loves the hidden world of trucking. Your support helps us keep telling these stories. The Dalton Highway begins north of Fairbanks, Alaska, at a junction most people would drive past without a second thought. From there, it stretches 414 miles north through terrain that becomes increasingly indifferent to human comfort. Crossing the Yukon River at mile 56, climbing past Coldfoot Camp at mile 175, pushing up through Adigan Pass at the top of the Brooks Range, and finally, descending to the frozen coast at Deadhorse near Prudhoe Bay, where the Arctic Ocean sits locked under ice for most of the year. There is no other road like it in the United States. In winter, truck traffic on the Dalton increases. While the summer months bring roughly 160 trucks per day, the winter months push that number closer to 250. The reason is not complicated. Ice roads and frozen ground allow heavier loads to move north to support the oil fields at Prudhoe Bay. The ground becomes harder, more stable, and so the trucks keep coming. Through darkness and blizzard and temperatures that the rest of the continent will never experience. The fuel available on the entire length of the Dalton is found in only 3 locations. The Yukon River Bridge crossing at mile 56, Coldfoot Camp at mile 175, and Deadhorse at the northern end. Between Coldfoot and Deadhorse lies a 240-mile stretch with no services of any kind, no fuel, no mechanic, no shelter beyond what a driver carries with them. It is the longest stretch of road without services anywhere in North America. If something goes wrong between those 2 points, help is not close. Help is hours away, across terrain that can kill an unprepared person in under an hour. Most people, hearing this, would assume that stopping the engine to conserve fuel would make sense. Save what you have. Reduce consumption. Be efficient. But that assumption is based on a fundamental misunderstanding of what happens to a diesel engine and the fluid system surrounding it when the temperature falls far enough below zero. Diesel fuel is not a simple liquid. It is a complex mixture of hydrocarbons, and one of the compounds naturally present in that mixture is paraffin wax. In warm conditions, that wax stays dissolved and fluid, moving through fuel lines and injectors without any resistance. A diesel engine at operating temperature never has to worry about the wax inside its fuel. But as the temperature drops, the wax begins to change behavior. Around 15 degrees Fahrenheit, it starts to crystallize. The fuel develops a cloudy appearance, something engineers call the cloud point, and small wax crystals begin forming inside the tank and throughout the fuel system. If the temperature continues to fall, those crystals grow. They clump together. They thicken the fuel into something with the consistency of soft candle wax. And once that happens, the fuel can no longer travel through the fine passages of a diesel injector. The engine cannot receive the fuel it needs. It starves. In the trucking industry, this process has a name. It is called gelling. And on the Dalton Highway in January, at temperatures that routinely fall past -40 and occasionally push past -50, gelling is not a remote possibility. It is an inevitable outcome for any diesel fuel left motionless inside a cold tank long enough. Here is what makes this particularly dangerous. Experienced drivers and fleet managers across the Arctic region know that standard number 2 diesel, the most common highway fuel, can begin showing cloud point behavior at around 15 degrees Fahrenheit. Full gelling, where the fuel can no longer flow at all, happens somewhere in the range of 10 to 20 degrees below zero for untreated fuel. Number 1 diesel, a lighter formulation sometimes called kerosene grade, performs better, with a significantly lower cloud point. Winterized blends, mixtures of number 1 and number 2 diesel with chemical additives, can push that threshold lower still, sometimes as far as -25 or 30 degrees with proper treatment. But at -50, even treated fuel faces serious risk if it is sitting still inside a system that has gone cold. This is why the engine stays running. A running engine circulates warm fuel through the system constantly. The heat generated by combustion travels through the fuel return lines back to the tank, warming fuel that is being sent back from the injectors. The system keeps itself warm from the inside. The moment the engine stops, that warmth disappears, and the fuel that remains in the lines, in the filters, in the fine passages of the injection system, begins cooling down toward whatever temperature exists outside. At -30, that cooling happens quickly. At -40, it happens in minutes. At -50, the fuel in an unheated system can begin gelling before a driver finishes a meal inside a warm building. But fuel gelling is only the first problem, not the only one. When a diesel engine sits cold at extreme temperatures, the engine oil changes as well. Oil viscosity, its resistance to flow, increases as temperature drops. An oil that moves freely at normal operating temperature becomes thick and sluggish when cold. And at extreme Arctic temperatures, it can become almost gel-like itself, so heavy that the oil pump struggles to push it through the engine's narrow passages during startup. The engineering term for what follows is dry start, a brief period during startup when critical engine components are moving against each other without adequate lubrication, simply because the oil has not yet reached them. Under normal circumstances, this dry start window is short enough that it causes no real harm. But at -50 degrees Fahrenheit, with oil that has been sitting motionless in an unheated engine for hours, that window extends. And in those extended seconds, metal moves against metal without protection. Experienced Arctic truckers describe this in practical terms. An engine that has never been allowed to go truly cold in -50 weather is an engine that starts reliably, runs smoothly, and will make the next delivery. An engine that has been shut down in those conditions and then forced to restart without adequate preparation is an engine making promises it may not be able to keep. The air brake system presents a third problem that most people outside the industry never consider. Commercial trucks use compressed air to operate their brakes, a system that requires the air compressor to continuously draw in ambient air and compress it. In extreme cold, moisture in that air condenses inside the brake lines and reservoirs. If the system is not actively working to cycle that moisture out, it can freeze inside the valves and lines. A frozen air brake system does not operate correctly. It can lock up. It can prevent pressure from building. It can create a situation where the brakes engage when they should release, or fail to engage when they should activate. On a road like the Dalton Highway, with steep grades and unpredictable ice, a brake system compromised by moisture freezing inside it is not merely an inconvenience. It is a catastrophic risk. A running engine keeps the air compressor working. It keeps warm air cycling through the system. It prevents the freeze-up that a cold, static system will develop when temperatures fall deep enough below zero. There is another dimension to this that goes beyond the mechanical. The sleeper cab of a modern semi-truck is, among other things, a survival shelter, insulated against the cold to a degree that most people would find remarkable. Equipped with a bunk heater that burns diesel fuel at a fraction of the rate the main engine consumes it. Stocked with blankets and food and emergency supplies. The sleeper cab represents a driver's primary protection against the environment outside. Modern auxiliary power units, small diesel-powered generators mounted beside the main engine, can run the cab's climate systems without running the main engine. They consume roughly 1/4 gallon of fuel per hour, compared to the main engine's consumption of somewhere between 1/2 gallon and 1.5 gallons per hour at idle. In many parts of the country, APUs have made all-night main engine idling largely unnecessary. Regulations in states like California and others have pushed hard to reduce truck idling, and APU technology has made those regulations workable in mild and moderate climates. But on the Dalton Highway in January, the calculus changes. An APU does a reasonable job of keeping the cab warm. It does nothing to keep the main engine warm. It does not circulate fuel through the main engine system. It does not keep the engine oil at a temperature that allows normal startup behavior. It does not cycle moisture through the air brake system. So even a truck equipped with a functioning APU, a good one, properly maintained, may still require the main engine to idle through the night when temperatures fall past certain thresholds. Not for the driver's comfort, for the truck's survival. The numbers involved are not trivial. An idling semi-truck engine burns somewhere between 0.6 and 1.5 gallons of diesel per hour, depending on the engine, the idle speed, and the conditions. Over a 10-hour rest period, that can represent 8 to 15 gallons of fuel consumed while the truck sits still. At current diesel prices, that translates to somewhere between $40 and $60 spent overnight, every night, doing nothing but keeping the engine alive. Over a winter season, across a fleet of trucks operating on routes like the Dalton, the fuel cost of cold weather idling is staggering. Some industry estimates suggest the average long-haul truck logs around 1,800 hours of idle time in a year. That is a volume of diesel burned not for transportation, but for preservation. And yet the alternative, in truly extreme conditions, is worse. Because when a truck breaks down north of Coldfoot in January, the situation transitions quickly from inconvenience to emergency. The nearest medical facility beyond Coldfoot is at Deadhorse, roughly 240 miles further north. South of Coldfoot, Fairbanks is about 175 miles away. Cell phone coverage along much of the Dalton is non-existent. The corridor uses CB radio for communication between drivers, and satellite communication devices are standard equipment for serious Arctic operations. When a driver radios in a breakdown between those fuel stops, the response time from any form of meaningful mechanical assistance can be measured in hours, not minutes, hours. In that waiting period, the environment does not pause. At -50 degrees Fahrenheit, exposed skin can experience frostbite in under 10 minutes. A vehicle that has lost its engine heat, with no functioning APU or bunk heater, becomes cold from the inside within an hour or two. A driver who has not prepared for a static survival situation, with adequate sleeping bags rated for extreme cold, emergency food, hand warmers, a communication device capable of reaching help, faces a situation that the Alaskan wilderness has been claiming without hesitation for a very long time. This is the geography of risk that shapes the decisions drivers make on routes like the Dalton. The decision to keep the engine running is not laziness or indifference to fuel costs or environmental impact. It is a considered professional judgment about which risks are acceptable and which are not. In conditions where the cost of a mechanical failure is potentially a human life, the cost of idling fuel becomes secondary. The ground beneath the Dalton carries its own memory of exactly how cold this corridor can become. At mile 135, just off the highway where the Jim River and Prospect Creek converge, a weather station recorded a temperature on January 23, 1971, that still stands as the coldest ever officially measured in the United States. The thermometer read -79.8 degrees Fahrenheit. rounded in most historical accounts to -80. The workers at Prospect Creek camped that day, there to support construction of the Trans-Alaska Pipeline, recorded a high temperature that same day of -64. Not the low, the high. That record has never been broken in the United States. And the terrain where it was recorded is the same terrain crossed by the trucks that run the Dalton every winter. The same corridor where drivers make the same decision about whether to keep the engine running when the temperature falls past the point where turning it off becomes dangerous. Modern engines have improved dramatically in their cold weather starting capability. Engine block heaters, electric resistance heaters that warm the coolant surrounding the engine block, make a significant difference when shore power is available. Trucking companies operating in the Arctic typically require their drivers to plug trucks into shore power whenever it is available at a stop that has it. Block heaters keep the coolant warm, which keeps the engine warm, which dramatically reduces the dry start wear that cold startups create. Fuel heaters, small electric elements that warm the fuel filter housing, prevent wax crystals from accumulating in the filter. Heated fuel tanks, common on trucks built for northern operations, use engine coolant routed through the tank to keep the diesel from ever reaching its cloud point. But these tools all require infrastructure. They require a plug to connect to, or a functioning auxiliary system, or an engine that has been maintained through the night. On the open road between Coldfoot and Deadhorse, where there are no buildings and no services for 240 miles, those options do not exist. The engine is the heater. The engine is the fuel management system. The engine is the brake system maintenance. The engine is, in a fundamental and non-negotiable way, the reason the driver inside will still be warm and the truck will still be functional when morning comes. Experienced Dalton drivers carry their knowledge of this corridor in a way that cannot be fully captured in regulations or safety manuals. They know which pullouts offer natural wind breaks and which leave a parked truck fully exposed to the north wind that comes off the Brooks Range. They know how the temperature in the valley drops differently than on the ridge above. The cold air draining down into low areas and pooling there, sometimes 10 or 15 degrees colder than the exposed ground 100 feet higher. They know how ice fog forms when exhaust hits air that is too cold to absorb moisture. A dense, almost solid cloud that develops in the immediate vicinity of anything burning fuel, including a running engine, and that can reduce visibility in a parked area to nearly zero within minutes. Ice fog is one of those phenomena that most drivers south of the subarctic never encounter. It forms when water vapor from exhaust or any combustion source meets air cold enough to freeze it instantly, not into snow, but into a suspended cloud of tiny ice crystals that neither rises nor disperses. In Fairbanks, where it can form at temperatures below -30 degrees, ice fog has been thick enough to cause multi-vehicle accidents on city streets. Along the Dalton, where a parked truck might be the only source of heat and combustion for miles in any direction, the ice fog from a running engine can form a visible plume that marks the truck's position across the landscape like a beacon. It is a strange and disorienting sight. A truck sitting in its own cloud, the engine running, the driver inside waiting for conditions to improve. Drivers on the Dalton learn to manage these conditions with a discipline that comes from understanding the specific physics of their environment. They know that a fuel tank that drops below half full increases the condensation risk inside the tank. Airspace above the fuel allows moisture to accumulate, and that moisture can freeze in fuel lines and filters in ways that even treated fuel cannot prevent. The professional habit of topping off the tank at every opportunity is not mere caution. It is condensation management. They know that modern high-pressure common rail fuel injection systems, which have replaced older mechanical injection on virtually every truck built in the last 2 decades, are actually more sensitive to fuel quality problems in the cold than the older mechanical systems they replaced. The precision tolerances required by modern common rail injectors, operating at pressures that can exceed 30,000 pounds per square inch, mean that even small wax crystals or ice particles in the fuel can cause damage that older, lower pressure systems would have tolerated without issue. The same technology that makes modern diesel engines cleaner, quieter, and more fuel efficient also makes them more vulnerable to the kind of fuel contamination that extreme cold produces. And they know that diesel exhaust fluid, DEF, the chemical used in modern emissions reduction systems, freezes at approximately 12 degrees Fahrenheit. Most modern trucks have in-tank DEF heaters to prevent this, but running low on DEF in extreme cold creates the additional risk of the reserve supply freezing before it can be added to the tank. A truck that cannot maintain its emissions systems may enter a reduced power mode that limits its ability to manage grades and maintain speed. On Atagun Pass, with grades approaching 12% and ice on the road surface, reduced power is not a minor inconvenience. It is a safety issue with serious consequences. The engine stays running because the fuel needs to stay warm. The engine stays running because the oil needs to stay fluid. The engine stays running because the air brake system needs to stay functional. The engine stays running because the cab needs to stay at a survivable temperature. The engine stays running because the possibility of it not restarting, out there, in that temperature, in that isolation, is not a risk that can be managed once it happens. It can only be prevented before it does. And so, the Dalton Highway in January sounds like this. The low, continuous rumble of engines that never quite go silent. Truck after truck parked in the pullouts and gravel areas between Coldfoot and Deadhorse. Each one maintaining its idle. Each driver inside managing their rest break and their fuel and their knowledge of what the next 100 miles requires of them. The machines and the people inside them are both in a state of active maintenance, never quite switching off, never allowing the cold to fully arrive. There is a kind of respect embedded in that sound, the sound of preparedness, the sound of professional judgment applied at scale across the longest unserviced stretch of road in North America, in the same terrain where the coldest temperature ever recorded in the United States was measured more than 50 years ago and has never been surpassed. The next time you hear someone complain about a truck idling in a parking lot in January, remember that somewhere along the Dalton Highway, far north of the Arctic Circle, in a darkness that lasts 20 hours a day in the depths of winter, there is a driver in a sleeper cab listening to that same sound and depending on it. Not just for warmth. For everything that has to work correctly when they wake up and point that truck north again toward Deadhorse. And if the Arctic is only part of the story of extreme temperature trucking in North America, wait until you see what happens when truck drivers are forced to operate during wildfire season. When the choice is not between cold and survival, but between smoke and visibility, and the road ahead can disappear for reasons that